Hi guys, Mr. Kane here.
Hi guys, Mrs. G.
And we're doing Thermo Stoich today.
Oh, I get the feeling this is going to harken back to first semester stoichiometry, Mr. Kane.
Yeah, I think so, because I remember Stoich. Stoich means stoichiometry.
Yep, mole-to-mole ratio, and this one's going to be just a tad different.
And mass-to-mole ratio?
Yep.
Yeah, okay.
Volume?
Yep, okay. All right, so let's see how this is different. All right, so we have enthalpy with different reaction types, right? Just as a reminder, if the delta H value is positive, that means that the reaction requires energy, or that the energy is written on the reactant's side of the reaction, right? And therefore, we've got an endothermic reaction. If delta H is a negative value, that means that the reaction makes energy. Energy is written on the product side of the reaction.
It's exothermic.
And it's an exothermic reaction.
Now, there are two ways we can write these kind of thermodynamic reactions, Mr. Kane. Do we have those anywhere?
Oh, do you mean like this one?
Yes, that's our most popular way of writing a thermochemical equation with the delta H to the right and the sign indicating whether it's endothermic or exothermic.
So the delta H is on the right side, so does that mean that it's a product?
No, it just on the right side of the reaction, just kind of piece of information. It is not part of the body of the reaction.
So if it's just a piece of information, that means it's a negative delta H, which means it's exothermic.
Exothermic, right.
Okay,
It's just a little piece of information written to the right of the actual chemical reaction.
Okay.
Or physical change, for that matter.
All right. Oh, yeah, you could do physical changes as a reaction, right?
Energy is transferred on all types.
Okay. What about if the delta H is written like this?
Well, it's still the same most popular type of thermochemical reaction. It's the way you'll see it most often. The delta H is to the right of the reaction as a piece of information.
And I notice here that the delta H is a positive value, 2,226 kilojoules.
That means it's an endothermic reaction.
Okay.
And requires, wow, that's got a lot of energy to require to break up those bonds between the carbon and the oxygen and the hydrogen and the oxygens.
Yeah, it is a lot. It is a heck of a lot of energy.
2,226 kilojoules. Think of that, what that is in joules. Woo!
Well, matter of fact, I think that this is photosynthesis.
Ah, so that's a lot of energy from the sunlight, yeah?
So that's a lot of energy from the sunlight getting turned into bonds in this sugar, which eventually we eat.
Yep, and
right?
it turns into energy.
And we get the energy from it, and we use it.
Yeah. There's the second way, not as popular as the first. There's the second way where they include the energy, the value of the energy, in the body of the reaction.
And now I've actually got to think about it.
Right.
Energy is a product. Therefore, the reaction is making energy. If it's making energy, it's exothermic.
Right.
Because the energy is coming out of the reaction.
That's that excess energy.
That's why it's written on the right, is
Correct.
because it's excess.
It's being released,
extra.
right.
Right, okay. And then there's this method, which is the same as the previous.
Right. It's showing the energy in the body of the reaction.
But the energy is on the left side of the reaction, which is the reactant side.
It's endothermic. You need an outside source of 393.5 kilojoules for that reaction to occur.
Because this reaction needs the energy in order to happen.
Correct.
Right. All right, so what does this mean?
Oh, I know.
Well, what does it mean, Mrs. G?
That means that chemical reaction there, which is a synthesis one, first semester information, is got energy on the right. It produces excess energy. Therefore, that is going to be an exothermic reaction.
All right, and so if I took hydrogen and bromine and I combined them together, not only would it make hydrobromic acid, but it would also actually heat up as it did that.
Yep. So we'd feel heat coming from the system.
Here's a good question.
Oh, this looks like stoichiometry.
Looks like stoichiometry. Don't get too scared here, Mrs. G, because
right.
Don't get too excited, actually, because there's not a lot of math here. If 1 mole of hydrogen is reacted with plenty of bromine, how much energy is produced?
Well, isn't that what the reaction says?
I guess it is, isn't it? The reaction, if you remember back to first semester, 1 mole of hydrogen plus 1 mole of bromine makes 2 moles of hydrobromic acid plus 36.4 kilojoules. So if I use only 1 mole of hydrogen with plenty of bromine, that means I'm going to use up all my hydrogen. I'm going to get exactly 36.4 kilojoules, right? If on the other hand I had 2 moles of hydrogen, now we're doing math.
Now we're doing math. Well, if I remember from when we used to do regular old stoichiometry, we used to start with the number given in the problem, correct? Okay.
So
start with 2 moles of H2, a number, a
2
unit,
moles.
and an identity. Wasn't it how we taught it?
Mm-hmm. number unit identity.
Now go back to the...
I need moles of hydrogen on the bottom, right?
Right, and according to the thermochemical equation, 1.
Right, 1 mole because of this, right? And hey, I bet I don't need to convert to any other type of matter, right? I don't have to convert to another substance. I can convert to energy because I know that 1 mole is 36.4 kilojoules.
Yep, you're just kind of doubling the recipe, therefore you're doubling the energy, aren't you?
So the math turns out to be 72.8 kilojoules, right?
Yep.
And so the big deal here is that we now have a mole energy ratio that can be found
from the
balanced equation.
Thermochemical equation.
So we could say 1 mole of hydrogen is proportional to 36.4 kilojoules of energy.
And you can do it for all the substances.
We could say 1 mole of bromine, Br2, is equal to 36.4 kilojoules in this equation. Or we could say that 2 moles of HBr is worth 36.4 kilojoules of energy, right?
Yep.
So we get 3 ratios that we could use from this one equation.
I can give you any quantity of any one of those substances and you can tell me how much energy is released. And just because you're burning more or using more or producing more, that's not going to change the fact that it's exothermic. This is still an exothermic reaction, whether it's 2 moles of hydrobromic, 8 moles of hydrobromic, or 132 moles of hydrobromic. It's just the quantity changes.
Right.
All right, so we're going to do an example of thermochemical stoichiometry.
All right, so how much heat will be released? So we want to know how much energy, right?
Right, you want to know how much energy
kilojoules.
and released because, again, you're not changing. It is an exothermic reaction.
Oh, look.
I see a negative sign.
In that second line, it says 6.44 grams. It doesn't say moles.
Way back ages ago.
I think I remember this because we were just doing this in the last chapter. We were doing well, actually 2 chapters ago, we were doing molarity.
Yeah,
and we had to take
from
mass to moles,
mass or mass
right?
to moles. Oh, can you do me a big favor, Mr. Kane? Can you put an identity in there?
There we go. Grams of sulfur.
Thank you.
We need to go from grams of sulfur to moles of sulfur, and 1 mole.
32.07.
Molar mass of sulfur.
Okay, so we've just converted from mass to moles.
So
we're used to that.
Grams are canceled. Moles are still here.
Yep.
Now that I'm in moles of sulfur, I can see that 2 moles of sulfur make 791.4 kilojoules, right?
Yep.
So I'm going to put 2 moles of sulfur on the bottom and 791.4 kilojoules. Now, Mrs. G, does it matter if I include that negative sign on the 791.4?
No, because it's not going to change the direction. It's still going to be released.
Right. So it's just when I come up with a negative, if I do include the negative.
You're going to come up with a negative value. It's just more energy being released.
And negative is just telling me released.
The negative sign just tells you direction.
If I already know it's released, I don't need the negative sign.
Right. Okay, so you get 79.5 kilojoules of energy released when you react 6.44 grams of sulfur with excess oxygen.
Right. And like we had said before, whether you have the negative sign here on the answer or not, it doesn't matter because this is energy being released.
Yeah, it's released whether it's 6.44 grams or 644 grams.
Matter of fact, in the Moodle quizzes, are we going to require them to put negative numbers?
No.
No. We'll always put energy in as a positive value.
As long as it's established already as being endothermic or exothermic, it's just a quantity difference. That's all. Not a direction.
So energy is always going to be written for us in the Moodle quizzes as positive.
Yeah.